皆さんこんにちは。お昼休みの食べた後でちょっと眠いかもしれない中、こちらにお運びいただきましてありがとうございます。皆さんのご発表では最初だけ英語でご挨拶されている方が多かったので、私の発表では最初だけ日本語でちょっとご挨拶させていただきました。So most of Japanese people talk in English as the first contact. So I try to say hello in Japanese, but this presentation I will present in English. So please enjoy. So today I'd like to talk about garbage collection in Ruby, more specifically how we can move toward Ractor local garbage collection for better concurrency and performance. So let's get started. So let me start with the conclusion of this talk. So introducing Ractor local GC is promising direction, but it's also a very challenging one. The biggest issue is cross-Ractor reference. As soon as objects start being shared, things get complicated. So we propose a conservative approach. We track all shareable objects and treat them as GC roots. As long as the number of such objects is small, this is a feasible approach. It behaves the same as the current garbage collection, which always does global garbage collection. So we've observed significant performance improvement in micro-benchmarks with this approach. So I'll explain how we got to this point in the following slides. Before going into the technical details, I want to acknowledge that the work is collaboration with Rohit Menon. He was a Google Summer of Code developer in 2022. And I had the pleasure of mentoring him on a project titled Optimizing Garbage Collection for Ruby Ractors. So this is the first step of the first trial of the Ractor local garbage collection. I initially proposed the core ideas and we discussed it together. So Rohit continued developing his own implementation, extending my idea over the next 3 years. I learned from his experiments and developed my own garbage collection. So today I present my own presentation, but this presentation is the collaboration work with Rohit. Let me introduce myself. So over the years, I'm Koichi Sasada. Over the years, I worked on several parts of Ruby implementation, and also I'm a director of Ruby Association since 2012. And also an owner of the bookstore at second floor. Thank you for coming and buying many copies of books. So before diving into the garbage collection, let me mention about my proposal changing the Ractor API in this ticket. So the idea is to introduce a new communication primitive called Ractor port and duplicate the current Ractor yield and Ractor take pair to communicate to each other. Conceptually, Ractor port is a small enhancement of the mailbox concept from the actor model. It provides a clearer, and more explicit interface for communication between Ractors. So today's developers meeting, so today's morning session, so there are many compatibility discussion, but the Ractor showing the warning. So this feature is experimental the feature, so we can change the API easily. So, okay, let me give you some background on the garbage collection for the Ractors. So Ractor was introduced in Ruby 3.0, a new concurrent model. It was changed to enable two things. So at first, the parallel computing on Ruby to take advantage of parallel computers for faster Ruby applications. Second, robust concurrent programming. So as you know, the thread programming has many issues. So with Ractor's isolated object spaces we provide, and we can avoid common concurrency bugs, especially those caused by shared mutable state. So overall, Ractor gives us the safer and faster way for concurrent programming in Ruby. So threads inside a single Ractor still need to acquire the GVL, which means threads in Ractor don't run in parallel, and one thread in the Ractor can run in Ruby code at a time. However, each Ractor has its own GVL, and threads in different Ractors can run in parallel. So on the parallel computers, such as the multi-core CPU, threads in Ractors 1 and Ractor 2 can be scheduled independently and actually run at the same time on different cores. Each Ractor has, in Ruby has its own isolated object space in logically. That means that every object belongs to the exact one Ractor, and it cannot be accessed directly from other Ractors, basically. So here is a very important rule about Ractors. So basically, you cannot access object in other Ractors. This means that the Ractor 1 can't read and write object from the belong to Ractor 2. So this strict isolation guarantees thread safety and avoid bugs from shared mutable state. This is the foundation for Ractor's robustness and safety. Now, if each Ractor has its own isolated object space, then it seems natural to run garbage collection independently or in parallel in each Ractor. In the slide, so each Ractor has its own root, and we can mark the all object in each Ractor and can garbage collection independently and in parallel. So this idea, what we call Ractor local garbage collection, today I want to propose. And on the surface, it seems like very natural optimization. So it's not strange one. However, so this is a problem. So Ractors can share certain objects called shareable objects. So these include classes and modules, frozen objects that only reference other shareable objects, and some special classes such as Ractor objects themselves. So in this example, both Ractor 1 and Ractor 2 are holding references to the same shareable object, this red one. And this is allowed. And that totally fine. This is allowed. And so while most objects are isolated per Ractor, shared objects act as exceptions and can be referenced safely from multiple Ractors. Now here is a key question. So if we allow each Ractor to run garbage collection independently, how should we deal with shareable objects? So let's walk through this simple example. So step 1, Ractor R1 owns a shareable object here. And second, the Ractor 2, R2, has a reference here, this one, to the SH1 object. And when R1 learns its local garbage collection, it doesn't seem reference to SH1 from within R1. So in R1, there is no references to the SH1. So garbage collector mistaken to free the SH1. But we shouldn't free the SH1 because R2 needs this SH1 object. So this is a problem. So with that background in mind, so let's move to the main challenges of implementing the Ractor local GC. So the first idea or ideal idea is to track the reference to the shareable objects across Ractors. So if R1 knows the SH1 is reference from other Ractors, then we can care about this reference, and the SH1 can be kept from freeing. So in this example, SH1 is only reachable from R2. So the challenge is how to maintain the reference information so the SH1 is reference from the other Ractors. So in theory, tracking reference between Ractors sounds reasonable, but in practice, it's very difficult. References can be updated at any time, and Ractors run in parallel. So this makes it hard to keep the reference state accurate across all Ractors. And if the tracking information becomes outdated or incorrect, the garbage collector might miss a reference and accidentally free a live object. So also from a performance perspective, tracking these inter-Ractor references can introduce speed and memory overheads. So let's talk about the tricky simple sample scenario. First, imagine that the SH1, a shareable object, is sent from Ractor 1 to Ractor 2, and Ractor 2 holds a reference to the SH1. And so we send the object, so the runtime detects the reference, so reference is passed to the Ractor 2. So we can mark the SH1 as a marked reference. So reference to level to the SH1, and that information is now used to avoid freeing SH1 during GC in Ractor local GC in Ractor 1. So there is no problem now. And now Ractor 2 reference the SH3 because we can reach the SH3 from SH1. But here is the problem. The reference tracking reference tracking information still says SH1 is referenced, so not a reference to the SH3. And it hasn't been updated to include this new reference to SH3. So now SH3 will marked correctly because, so in this case, so the SH1 is marked as a reference. So the traversing marking correctors marks this is so SH1, SH2, SH3 is a living object, and there is no problem just now. So the problem is if the SH2 removes the link to the SH3, so there is no information that the SH3 is should not be freed. So it means that the Ractor local GC at the R1, SH3 can be freed, and after that, if the Ractor 2 tried to use the SH3, it was freed and it caused a very bad issue. So if we pay many effort or many overhead, we can get a reference from the object SH3 reference to the SH3, but there are many facts that we cannot introduce such a mechanism. So this is a challenge. So let's not solve this challenge. So because solution one seems difficult, and we were using the global object space just now, so the current master branch or from Ruby 3.0 to the Ruby 3.4 and master branch, it uses a global object space. So that means that there is no parallel heap. All objects, whether created in R1 or R2, managed together. When we need to run the garbage collector, Ruby has to stop all Ractors and then traverse from all routes marked live objects. This is accurate, no problem, but it's never but it is slow because we need to stop all of the object and all of the Ractors, and we need to traverse all of the objects between Ractors, and also we can't utilize the parallelism. So this slide compares the timeline of the two GC strategies. So solution one, local GC, and solution two, the current global garbage collector. So in local GC, each Ractor runs garbage collector independently, and that allows GC to run in parallel. But as we've seen, it's difficult to implement. In contrast, the current global garbage collection solution 2 stop all Ractors. If one Ractor requests a pause, then the runtime waits until all Ractors are stopped and runs garbage collector on the shared heap. This is simple and space efficient because free slots can be shared between Ractors. But unfortunately, it's slow. And it broke parallel solution execution. So our goal is that we want to introduce the local GC to improve the performance and run garbage collection in parallel and independently for each Ractor, like how it's doing in Alan or Elixir languages. But the big challenge is shared objects, and it's difficult to track reference that goes across Ractors. And that's exactly why Ractor local GC has been missing for years. It's very hard to get it right. So the core challenge here is how do we design safe and practical algorithms that enable Ractor local GC without breaking anything. So now that we've seen the challenge and how do we safely implement Ractor local GC, especially with shared objects. So let's dive in. Our proposal is simple and conservative one. So we do not try to detect the reference of sharing objects. So it means that we assume that all of the shareable objects marked as shareable objects are living while local garbage collection. Because it's really hard to track cross-Ractor reference safely, so instead we assume the shareable objects are always alive during local GC. So this algorithm works because the number of shareable objects is enough small, and we treat them as root object during Ractor local GC. Then to correct the shareable object, when needed, we fall back to the global GC. So we already have a global GC, so we can reuse this one. So which pulls all Ractors and checks every references, as I said, so it is slow, but we can run global GC less frequently than current one. So this is why I propose this one. Ractor local GC will be enough, I think. So this figure shows how to share shareable object for each Ractor. We maintain a set of shareable objects. So during local garbage collection, we treat these as root objects and mark them as if they are always alive. So this is accurate. We never miss live references, but there is a trade-off. So if shareable objects are no longer reachable, won't be collected until global GC happens. So that means that memory for such objects may stay around longer, but the benefit is we can safely run GC in parallel per Ractor. So in practice, most of shareable objects are long-lived. For example, classes, modules, methods, and bytecodes are, of course, long-living objects. And Ractor objects themselves also tend to live longer. So maybe naturally, so the most of shareable objects will be long-lived objects. So we can, so we decided to employ this idea. So this is proposed timeline with our conservative approaches. So sometimes, so most of the case, so we run the local GC independently in parallel, and infrequently we need to use the global GC. So from this work, we learned the key insight. So done is better than perfect. So we can't introduce the Ractor local GC because solution one can't be completed. So we discussed several years, but so this today's proposal is not the best, but it improves the performance. So we need to introduce it fast, and after that we can discuss solution two. So this is my study of what I learned from this work. So I implemented the local GC with these steps, but let's skip details because there is no time to talk enough. So, so I do many things to do that. And we have many techniques to improve the performance, but I also skip this slide. So I will publish this slide. So if you have interest, please check it or ask me later. So from here, I'd like to talk about the evaluation we measure the performance of our proposal through the micro benchmarks, comparing it against the current Ruby implementation. So here is the benchmark environment. I use 14 cores with 6 performance core and 8 efficient cores of Intel CPU. For micro benchmarks, we repeat simple tasks n times across Ractors. So each Ractor performs Tn tasks where Tn defined as n divided by the number of Ractors. The benchmark script is available this GIST page. So first of all, we show the simplest one. So each Ractor repeat allocate short-lived string objects. So as shown in code snippet here, so it's just created and discard empty string Tn times on each Ractors. On the x-axis, it is the number of Ractors, and the y-axis we have execution time in seconds, so lower is better. And the blue line shows the current Ruby master, and the orange line is local GC version. You can clearly see that with more Ractors, our version scales better. So this is same benchmark as before, but we show looking at the speed up ratio compared with the single Ractor execution time. So higher is better here. As you can see, the orange lines for our modified version scaled quite well, achieving nearly 5 times speed up with 16 Ractors. In contrast, the master version shows almost no parallel benefits. That's because all Ractors are stopped for global GC, eliminating the advantage of parallel execution of Ractors. This result shows that the local GC work effectively for Ractor local short-lived with short-lived objects. So next example is making a long-lived object. So this calls the make many array, but the array doesn't read. So the master version shows the clear bottleneck. So as we increase the number of Ractors, the execution becomes worse, even if it's run in parallel. In contrast, our local GC version handles this very efficiently. So this is the speed up ratio of the last benchmark. So higher is better for same benchmark. Again, master branch doesn't scale. Performance actually gets worse with more Ractors. That's because every Ractor contributes to triggering global GC more frequently. In contrast, the local GC version continue to scale, achieving over 4 times speed up with 16 Ractors. This result shows how local GC helped long-lived Ractor local objects. Here is a benchmark run in simple regular expression matching. And it also shows good performance compared with the master one. So this shows the speed up ratio, and orange one is a modified version. So higher is better, and our local GC shows a good performance than the current one. So it includes the regular expression execution time, so it is not better than the last two examples, but it also have good performance compared with current one. So let's wrapping up today's topic. So we need to complete the implementation for Ruby 3.5 to introduce the Ractor local GC. So we have many tasks, and also we want to make a parallel marking on the global GC. So we have several cores, so we can utilize them. And also, so after that, we want to introduce the difficult solution one for more performance. So Rohit said he might have a good idea, and he implemented it. And he says that he has a good implementation for that, so we can wait for his great news after that. So this is a summary of this presentation. So I introduce why the Ractor local GC is difficult, and I propose a conservative approach, and it can improve the performance on the micro benchmark significantly. So question is, so at last, this work is collaboration with Rohit Menon. And so thank you for listening. So question and are very welcome. So please ask me later at the store's booth. So thank you so much.